So let's see 10.2 chlorine substituted acids. Okay, so that means now we have to compare, for example, CH3COOH with CH2Cl So you want to know who is stronger over here. So let's see the statement. Acidity of carboxylic acid increases when H atoms are substituted by electronegative atoms such as chlorine. So that means stronger. Who is stronger? The one with chlorine is stronger. This is weaker. So why? Chlorine atom shows a negative inductive effect, withdrawing negative charge from the molecule, reducing the strength of the OH. So imagine, the electron will go to the left because of the Cl. And this O is not so negative already because electron go to the left. So when the O is not so negative, then they cannot attract the hydrogens. Cannot attract the hydrogen because electron go to the chlorine already. So O not so negative and cannot attract the H. Okay, so H can go out easily, meaning that it can donate hydrogen ions more easily, and it also means that it is a stronger acid. Okay, so it's written here actually. Chlorine atom shows a negative inductive effect, withdrawing negative charge from the molecule, reducing the strength of the OH, and hence making H plus be lost more easily. Conjugate base is more stabilized due to the extended delocalization of the negative charge on the COO minus, and so less likely to bond with a H plus ion. So it means what? You see when they form ion, right? Okay, when this form the carboxylic ion, so it's CH3 and then CO. Okay, delocalization happen this way. But for the other case, CH2, I have to put like this. CCl, HCO. Okay, delocalization can happen here. Okay, so you can see the negative charge can delocalize to a bigger region. So the negative charge is more spread. Okay, then if it's spread, then it's not so negative already. So the H plus which is lost, don't want to come back so much already, because not negative enough to attract the H plus. So meaning that this is stable. And whenever we say the conjugate base is stable, that means the conjugate base is weak. Then the acid is strong. Okay, so you have to take notes on that. Now, let's see the next part. Note. If an electron donating group is present, molecule is less acidic. So for example, electron donating group is the LQ group. If you have a bigger LQ group, then it's less acidic. If an electron withdrawing group is present, for example chlorine, then the molecule is more acidic. Okay, so this is the conclusion. And now let's see the next one. 10.3 Oxidation of carboxylic acid. So let's do a quick revision first. What kind of oxidation is that? Last time in AS chemistry, we learned primary alcohol. You oxidize, then they form aldehyde. Aldehyde, you oxidize again, then they form carboxylic acid. And in AS chemistry, when they form carboxylic acid, then end of story already. But now, 10.3 say that we can continue to oxidize it. So we can continue to oxidize it to CO2 and H2O. But the thing is, not all the carboxylic acid can do these reactions. Only two special carboxylic acid can do oxidation. So the special carboxylic acid here is the metanoic acid. The metanoic acid, what is metanoic acid? Is HCOOH. Okay? HCOOH can oxidize to form CO2 and H2O. So what is so special about this metanoic acid? This metanoic acid, right, it is special because it looks like, okay, let me draw out first. Okay. You may think of something like Tollens reagent, sphaling reagent. Isn't this aldehyde? Yes, it's true, aldehyde. So if you look at metanoic acid, right, you may think of its structure is like the aldehyde on the left, and on the right, carboxylic acid. In AS chemistry, we learn aldehyde can react with Tollens reagents, can react with Fehling reagents, where aldehyde is oxidized to carboxylic acid. That's what we learn in AS chemistry, on the aldehydes that react with Tollens and Fehling. So now, what happened then? It can react because they have this C double bond OH, so which is the aldehyde, aldehyde structure. So with Tollens reagents is the silver ion, silver ion in ammonia. So silver ions get reduced to silver mirror is formed, and then the imagine it's supposed to form COOH on the left also. So if you have COOH on the left and on the right, then it's not stable, then they break down to CO2 and H2O. Okay, with Fehling solutions, Cu2 plus get oxidized and get reduced to Cu plus, and then again the aldehyde part get oxidized to C double bond O. This side should become OH, but OH on both sides is not stable, and it forms H2O and CO2 then. So notes, can use stronger oxidizing agent like the common one, potassium manganate. Potassium manganate 7, acidified potassium manganate 7, or acidified potassium dichromate 6 can oxidize the aldehyde also. Okay, so the next one, ethane dioxide acid. Ethane dioxide acid is a carbon with COOH on the left and COOH on the right. This one is different from what I discussed just now. I say OH on the left and OH on the right. That is not stable because OH on the same carbon. But OH on different carbon is okay one. OH on this carbon, OH on this carbon, this is better. This is more stable. Okay, so this is ethane dioxide acid. So react with oxidizing agent, then they form CO2 and H2O. This time you can't use Tollens or Fehling because no aldehyde group. So you must use a stronger oxidizing agent like potassium dichromate. Potassium manganate 7 with acid. Then it is strong enough to oxidize it. Strong enough, huh? So the purple or the pink color will change to colorless. You can also use acidifier potassium dichromate 6. Then the color change from orange to green. Okay, so they form the same product, CO2 and H2O. It seems like nothing more already, but I have to add one more note for you. So we have to know that if you have carboxylic acid, just now they said carboxylic acid can oxidize to CO2 and H2O. They can oxidize. So now we are going to talk about this part actually. Can carboxylic acid reduce or not? Reduce. Okay, reduce, I put H. Reduce. So we want to discuss this part. Carboxylic acid can reduce to aldehyde or can reduce to alcohol or not. So we want to see whether it can happen or not. Theoretically can, right? If you can oxidize, then you can go backward, reduce. So actually, yes, we can reduce it. So carboxylic acid, you use reducing agent, this one, lithium aluminium hydride, then that will form primary alcohol. Okay, primary alcohol. So if just for your information, amide, we will learn it later. Amide can go through reduction also. LiAlH4, then they will form something like this. So maybe you know a little bit, or maybe you are not sure what happened here. Okay, so I give explanation first. The idea of reduction is the C double bond O will receive hydrogens in this way, and because of that, they will either form primary alcohol or this structure. Okay, let's see carboxylic acid. Carboxylic acid is C double bond O, O, H, and R. Okay, now you focus on the C double bond O itself, then you put hydrogen up and down. So this is primary alcohol. For amide we learned a little bit just now, CONH. Let's say here don't know what, prime. Okay, so you focus this alone, and then you put hydrogen to it, NH, prime. So that's why we have that kind of structure. So okay, that is the reductions. So we finish up the theory already.